In previous sections of the course, I presented a method for calculating the thrust generated by a scramjet using control volume analysis. It's the method used by engineers all over the world for calculating the performance of air-breathing engines. To revise, we developed the deceptively simple equation shown here for calculating scramjet thrust. Starting at the front of the engine, the terms used in the equation are Fn, the stream thrust of the air entering the engine. This depends on flight conditions and the free stream captures tube of the intake. Fad, the additive drag due to flow spillage and plume effects, and this is calculated by computational analysis or rules of thumb. And finally, Fout, the stream thrust of the air and combustion products that exit the engine. This last term is the one that we'll concentrate on here. To calculate it, we must follow the flow through the engine and analyse changes that occur during its passage. This can involve quite a bit of effort, but can be done at varying levels of complexity and accuracy. The flow analysis methods presented in the previous sections of the course will be used for this purpose. They provide the tools needed for a simplified but representative calculation of scramjet thrust. As air passes through a scramjet engine, it undergoes three distinct processes: compression by shock waves and flow contraction caused by the vehicle forebody and engine inlet, combustion with the injected fuel in the combustor, and expansion in the thrust nozzle. It is common practice to define numbered stations through the engine to aid in the analysis of these processes. Station 0 is in the free stream and is undisturbed by the engine. The air is first compressed by the vehicle forebody to station 1. Further compression is done by the inlet to station 2, which is called the throat of the engine and is its minimum area. Between station 2 and 3 is a short duct called the isolator, which isolates the operation of the inlet from pressure rise which may occur in the combustor. Station 3 is where the primary fuel injection occurs and defines the start of the combustor. Station 4 is the end of the combustor, and in most instances defines the end of the combustion process. In a scramjet, we go straight to station 10, which is at the exit of the vehicle. Stations 5 to 9 are not needed for scramjets. As already mentioned, analysis of airflow through a scramjet can be very complex. As a first step towards doing this, we will use some of the methods presented in earlier parts of the course as model for each of the processes. Firstly, compression. In this analysis, we will model the forebody and inlet as a two-dimensional three-shock process. We will include shock losses and assume full capture of the flow and that the additive drag is 0. Secondly, combustion. In this analysis, we will assume our scramjet has a constant area combustor and that the heat addition due to combustion can be modelled by Rayleigh flow. No accounting of viscous losses will be made in the combustor. Finally, expansion. The nozzle expansion will be modelled as isentropic with no losses. And the amount of expansion will be defined by the exit area, A10. Another important simplification that we will use is that all analyses will be performed using assuming flow of a perfect gas at constant ratio of specific heats, or gamma. In a real scramjet, gamma varies between 1.4 for air at low temperature to as low as 1.2 for the hot combustion products. The analysis needed to correctly model these effects is beyond the scope of the course. So compression. In order to burn fuel efficiently, the air captured by a scramjet flying at high altitude must undergo a significant compression. There are two key characteristics of any compression process. First, the capability, by which we mean how much compression is done by, in this case, the forebody and inlet. The amount of compression is characterized by the compression ratio between station 0 and 2. The second characteristic is the compression efficiency. Now this is measured by the stagnation pressure ratio between stations 0 and 2. In most situations, the capability of an inlet process is a requirement of the engine, whereas the efficiency is a measure of the quality of the compression. The higher the stagnation pressure ratio, the better and more efficient is the compression. So the goal of a good inlet is to capture as much airflow as possible with the least amount of stagnation pressure loss. Now, combustion. The mixing of fuel and air and then their chemical reaction to produce combustion products must occur during the time it takes the air to travel along the combustor. Much of modern scramjet research is concerned with finding better ways to make this happen. Examining the constant area combustor under analysis here, properties at station 2 and 3 will be identical. Fuel is added at station 3 and combustion is complete by station 4. The heat release from combustion is used to calculate an increase in stagnation temperature, which is then used in the Rayleigh flow equations. The heat release depends on a number of factors. First of all, the heating value of the fuel, which for hydrogen is about 120 megajoules per kilogram. Next, the stoichiometric ratio of the fuel, which for hydrogen is about 2.9% of the airflow. Next, the amount of fuel added must be defined, and this is in terms of the equivalence ratio. So just remember, the equivalence ratio of 1 corresponds to enough fuel to burn all the oxygen in the air. But we also need to worry about the combustion efficiency. That is, how much of the fuel we injected was actually burnt. And a realistic goal for this is 80%. Finally, expansion. The nozzle of the scramjet expands and reaccelerates the combustion products to generate thrust. We will assume a quasi-one-dimensional isentropic expansion from station 4 to a specified area ratio at station 10. Now once we've done this, we will know all the properties of the air and combustion products as they exit the engine. So how do we put all this together to get thrust? The first term in the thrust equation is the inflow stream thrust, Fin. It is calculated based on the properties at station 0, where V0 is the flight velocity. We can use the perfect gas relation to determine Fin in terms of P0, A0, M0, and the ratio of specific heats gamma. The other term in the thrust equation is Fout. Knowing all the properties at station 10, we can similarly determine the outflow stream thrust in terms of P10, A10, M10, and once again the ratio of specific heats gamma. So the thrust generated by the engine is simply the difference between Fout and Fin. In section 7 of the course, you'll have the opportunity to calculate the thrust of a scramjet using these methods.